One of the greatest challenges humanity faces today is the lack of a clean and endless energy, and the means with which to provide this energy, via nuclear fusion, for the world. The first step in achieving this goal is providing insight to the problems we are currently faced with. The world needs a clean and endless energy to protect the environment, our health, and the ozone layer. Coal, oil, and gas are examples of fossil fuels. They provide a large percent of energy today. They are readily available, and they are easily synthesized. Though fossil fuels serve great purposes in our lives today, they negatively affect the environment. When heated, they emit harmful materials such as carbon dioxide, carbon monoxide, sulfur dioxide, mercury, and other toxins. Coal, a dirty energy source, emits radioactive material, more than a nuclear facility. These toxins don't provide healthier living if they are polluting the air we breathe in each day. Also, these gases release additional greenhouse gases into the atmosphere that increase the warming effect. Another example is biofuels, which include sugarcane, corn, and vegetable oils. The plants that are used for biofuels absorb carbon dioxide and are easily renewable resources. However, the concern is that they do not reproduce fast enough and may use more energy than produced. It takes a large amount of energy to grow crops and produce fertilizers. Ethanol, a biofuel, is added to gasoline to burn cleaner, but has a higher evaporation emission when burned. These particles contribute to the ozone problems and smog. Similarly to fossil fuels, though slightly less, biofuels create harmful emissions and waste when burned. Nuclear fission is presently an option that creates no air pollution or carbon dioxide and produces much more energy than is input. The fuel and operating costs are inexpensive, and the fuel is recyclable. The process results in very few byproducts. All of the byproducts since 1950 could fit into a single football field today. Some of these spent fuels, however, are highly radioactive and require a special facility. Some waste will remain radioactive for thousands of years and prevent the reuse of contaminated land. Since they use large amounts of water for cooling, it can also harm the aquatic life. There is also the possibility of a reactor meltdown. Therefore, the possible solution to our problem, clean energy, must not have the same problems as the options we already have. Our solution should be safe by eliminating toxins, controllable so that we can safely start and stop the process, and renewable so that we may have a long-term solution. Now that we have identified the problem and the constraints, we may begin to explore the possible solutions for clean, endless, and renewable energy. Hydroelectric dams and tidal power use water to turn turbines. Wind turbines use wind energy to turn their blades and generate energy. Solar cells are used to absorb solar power and convert it into usable energy. Geothermal energy uses the thermal energy generated from the core of the Earth. Nuclear fission reactors split atoms and harness the energy released from the reaction. Nuclear fusion reactors combine two atoms and the energy is harnessed from that reaction. With all the possible options laid down, we may select the best approach to fusion. Nuclear fusion is the fusing of two atoms. This produces some energy, and in order for this to be a usable energy source, the reaction must produce more energy than is needed to start the reaction. The primary goal of nuclear fusion is to emulate the fusion that is constantly occurring in the stars. Currently, we are trying to fuse the heavy hydrogen isotopes deuterium and tritium. Means of accomplishing fusion include magnetized compression, in which magnets are used to compress the two atoms together, and laser-based confinement, in which many lasers are shot into a single spot, causing the fuel to condense and fuse. With a selected approach, we may construct the prototype to begin testing. There have been many advances with nuclear fusion since research started in the 1930s. In 1968, the Soviet Union developed the world's first nuclear fusion research facility. They called their reactor a tokamak and for the first time achieved the appropriate temperatures and plasma confinement times, two of the necessary components for fusion. The construction of the tokamak led to the construction of more advanced fusion research facilities around the world. NIF is just one of the many research facilities around the world. It began operating and experimenting in 2009 and uses laser-based inertial confinement to fuse atoms. In this particular facility, 192 lasers are directed at a fuel pellet to rapidly compress the nucleus. The International Thermonuclear Experimental Reactor is a joint effort of 7 nations. Their experimental research is to begin in 2018 and will use magnet chambers to compress and fuse atom nuclei. Scientists involved with this reactor expect the energy output to be 10 times greater than the input. The USA alone has many different experimental fusion reactors, including the Levitating Dipole Experiment, the Z-Inertial Fusion Energy Test Facility, the Lawrenceville Plasma Physics, FRXL, and Sonafusion. Around the world, there is the High Power Laser Energy Research Facility in Europe, General Fusion in Canada, and the Windelstein 7X in Germany. After the concepts and designs are refined, we may begin the design process again to better the solution for the problem at hand. Worldwide contributions have increased their efficiency as they attempt to achieve what is known as the plasma break-even point. This is the point at which the plasma's output energy equals the input energy. Though this point has not yet been reached, the joint European Torus facility has the record of achieving 70% input power. Fusion, or any energy source for that matter, is not efficient until the power output exceeds the power input. For this reason, fusion research has a ways to go until fusion is a viable commercial energy source. Engineers have a ways to go with the development and utilization of nuclear fusion, but with the design process, the grand challenge of clean, endless energy will be achieved.